Again, welcome to Unit 9, Part 1 lectures. These lectures cover the correlation and regression. Our main objective is to introduce the concept of linear correlation, independent and dependent variables, and also different types of correlation. We're also going to learn how to find the correlation coefficient and also how to perform hypothesis testing for population correlation coefficient rule. So what is a correlation? Here we say a correlation is a relationship between two variables. So a data can be represented by other pairs, X and Y. Now, X will be the independent variable and Y will be the dependent variable, which means S determine Y if there's a relationship between X and Y. Here we can plot what we call the scatter plot. So a scatter plot can be used to determine whether a linear straight line correlation exists between two variables. So for example, here we have values for X and Y. When we plot a scatter plot, this is what we get. And by looking at the pattern of our points, we can see that there's a linear correlation. And this linear correlation is an increasing correlation, which means when the value of S increase, Y also increase. Now, types of correlation, here we say that when S increases, Y will decrease. So this is called the negative linear correlation. By looking at the pattern, we can see that when X value is increasing towards the right, Y will be decreasing down. So normally Y is vertical, so increasing will be up, and S is horizontal, increasing will be towards the right, decrease will be towards to the left. So this will be a negative linear correlation. And this will be a positive linear correlation because we can see that when S increase, also Y increase. So when S is increasing towards the right, Y is increasing upward. So here again, we say as S increase, Y tends to increase. So this is a positive linear correlation. Here we have no correlation because we can see that some of the S values, it shows that when S increase, Y increase. Sometimes it shows that when S increase, Y decrease, or either opposite. So here we can see there's no pattern, the points just scatter everywhere. So there's no any correlation. And here we have nonlinear correlation. Actually, we can say this is a polynomial correlation, nonlinear. Our course again, lectures today focus on linear correlation. So we have example here. In this example, we are going to construct a scatter plot. And from the question here, we have a company advertising expenses and also the company sales for each year. So for example, 2.4, and we can see the company sales is 225. When it's 1.6, the company sales is 184. Again, these values are in thousand. So here to be 1,600, then we have 184,000 company sales. So what we're going to do is that we're going to display this data in a scatter plot, and most likely we can see the pattern. So this pattern looks like it's an increasing relationship, but not that perfect increase. Now, the correlation values always is between -1 to +1. So if it's close to 1 or it's 1, then it's 100% linear. When it's somewhere around 0.7, 0.6, it's still a increasing relationship and linear, but some of the points will not be on the line. So by looking at this part again, we can say there's an increasing relationship. So here we say it appears to be a positive linear correlation because as the advertising expenses increase, the sales tend to increase also. So again, this is increasing relationship. Next, we will go through what is a correlation coefficient. And normally the correlation coefficient, we can find it, and when we get the value, it will determine the strength of the relationship between the two variables. So here we say the correlation coefficient normally measures of the strength and also the direction of a linear relationship between two variables. Now, what we mean by direction is that normally the correlation coefficient, the value will be between -1 to +1. Now, if the value is negative, then we have a decreasing relationship. When S increase, Y decrease. Now, if the value is positive, close to +1, then we have increasing relationship. When S increase, Y also increase. Now, if the value is close to 0, then we don't have no correlation. There's no relationship between the two variables. So here we represent the correlation coefficients with a symbol R. So R represents the sample correlation coefficient. And to use the formula, we can use this formula to find the correlation coefficient. Now, N will represent the sample size. X and Y are the independent and dependent variables. That will be the data set that will be given to us. So with this formula again, we can find the R. Next, also, we can find what we call the population correlation coefficient. And we use the symbol rho to represent it. So now the range of the correlation coefficients, as we said earlier, is between -1 to +1. So if the value is close or is -1, then we have a perfect negative correlation, which means decreasing relationship. Now, if it's close to 0 or is 0, then we don't have no linear correlation. Then if it's close to +1 or is +1, then we have a perfect positive correlation, which is increasing relationship. Then we can see when S increase, Y also increase. Now here we can see that all the points are not on the line, the linear. So we may get maybe close to 1. In this case, we have -0.91. And we can see this is again decreasing relationship. As S increase, Y decrease downward. Here also the same thing. All the points are not on straight line. So we approximate R is 0.88. This is again increasing relationship. We can see the pattern that as S increase, Y also increase. Here also we have an increasing relationship, but we can see that we have some points that are very far away from the linear line. So that's why the R value increase. But we still have positive value and 0.42. So we will call this the weak positive correlation. Here we have non-linear correlation, and we can see the R value is close to 0. So those are the different types of, again, correlation coefficients. Now, how do we calculate the correlation coefficient? Again, we saw the formula in our previous slides. First thing we should do is to find the sum of the X values. Then we also find the sum of the Y values. The reason why, because we are going to use these sum values in the formula. Then next, we also have to find the sum of the product of X and Y. So after we find the sum of X, sum of Y, we multiply the two together. That gives us the sum of the product of S and Y. Then we can find the sum of S squared, which means we square all the S values, then we sum it. Then we also find the sum of Y squared. We square all the Y values, then we sum it. Now we can see the formula now. We can plug N is the sample size. We already find the sum of XY minus the sum of X, the sum of Y, which we found already. We have the N. We also find the sum X squared minus, now there is a difference between sum of S squared or sum S squared, sum X all squared. Now sum S squared, sum X all squared means we find the sum of X, then we square it. But S squared sum means we square each S value, then we sum it. So the two will give us different answers. Same thing applies to the Y. We find the Y squares and we sum it. By here, we sum the Y, then we square the value. So now we have all the values we plug in, then we get the value of R. So this is an example Again, since advertising expenses would determine the company's sales, we are going to say that the S value should be the advertising expenses and the Y value will be in the company sales. So we again get our table X and Y. Next we find the XY. So we multiply X and Y together. We have 540, 294.5, 8.4. 2.0 times 220 will give me 440, etc. Then we sum all, and that gives us the sum of XY. Next, we find the S squared for each X values, then we sum all. Then the same thing, we find the Y squared for each, then we sum everything. Now we have all the values we need to plug in our formula. So we plug the values. The sample size is 8 because we can see this is 1, 2, 3, 4, 5, 6, 7, 8 events or 8 years. So we plug in the values and our R value is 0.9129. So here we have a very positive, strong linear correlation. So here we said that R is approximately 0.913, which suggests a strong positive linear correlation. As the amount spent on advertising increases, the company sales also increase. Next, also, we can use the table to test the population correlation coefficient rule. Here we say once the sample correlation coefficient R has been calculated, we need to determine whether there's enough evidence to decide that the population correlation coefficient rule is significant at a specified level of significance. So we can use, again, our textbook is table 11. We can use the table 11, then we can determine if R is greater than the critical value, then there's enough evidence to decide that the correlation coefficient rho is significant. So we're going to see an example soon. Here, the example is that we're going to use the table to test the population correlation coefficient. So here they say we should determine whether rho is significant for 5 pairs of data. N is equal to 5. Normally in this table, the N is given, and then we have the alpha values, either 0.05 or 0.01. So since N is 5, we go to the N5 row, and the significant is 0.01, then we go 0.01. So this means that our answer will be 0.959. Your question again said, determine whether rho is significant for 5 pairs of data, which is N equal to 5 at a level significance of alpha equal to 0.01. So here we say we are going to reject HA if rho equal to 0, if the absolute value of R, again, is greater than the value given in the table. So since R is greater than 0.959, we will say that the correlation is significant. Otherwise, there's not enough evidence to conclude that the correlation, again, is significant. So how do we use the table to test the population correlation coefficient? First, we need to determine the number of pairs of data in the sample, which means we need to determine the sample size. And then we have to specify the level of significance, which is the alpha value. That is 0.05, 0.10, etc. Then we can find the critical value using the table. So to get the critical value, we need the N value and also the alpha. So now when we get the critical value, we decide if the correlation is significant. And the only way we can decide is that if R is greater than the critical value, then we say that the correlation is significant. Otherwise, there's not enough evidence to support that correlation is significant. Then we need to interpret the decision in the context of the original claim. So let's see an example here. Here they say using the old faithful data, you use 25 pairs of data to find R equal to 0.979. Is the correlation coefficient significant using alpha equal to 0.05? Remember here they give us the n value already, 25. We know the alpha. And this is our data set for the whole 25. So first we use the table. As we said, the n is 25. Alpha is given to us to be 0.05. So we go to 25, 0.05. So that gives us 0.396. So now since 0.979 is greater than 0.396, which is our critical value from the table, we say that there's enough evidence at 5% level of significance to conclude that there is a significant linear correlation between the duration of old faithful eruptions and the time between eruptions. Now, if the critical value is rather greater, then we have it the opposite. There's not enough evidence. Next is hypothesis testing for population correlation rho. Here we say hypothesis testing can be used to determine whether the sample correlation coefficient R provide enough evidence to conclude that the population correlation coefficient rho is significant at a specified level of significance. So hypothesis testing can be again one tail or two tail. Now, if we have a left tail test, we say that the null hypothesis, the rho is greater than or equal to 0. No significant negative correlation. Or alternative or HA means the rho is less than 0. It's a negative correlation. The right tail means the rho or the HO rho will be less than or equal to 0, which means there's no significant positive correlation. Or the rho is greater than 0 means there's a significant positive correlation. Now, two-tail means rho not equal to 0 and rho equal to 0. So HO means it's equal to 0, HA means not equal to 0. So we have two ways. Now, a t-test for correlation coefficients also can be used. So here we say can be used to test whether correlation between two variables is significant. We can use the t-test to do it also. Now, in terms of test statistics, it will be the R, because again, here we are testing correlation coefficient. And the formula, the standardized test statistics, we say the T equal to R divided by, again, the standard deviation, which is the same as saying R. The standard deviation R here will give us square root of 1 minus R squared divided by N minus 2. This will follow the T distribution. The degree of freedom is N minus 2. So here we're going to use the T table. So here we say in this, our course textbook, we only use the two-tail hypothesis testing for rho. So using the t-test for rho, here first thing we have to state our null and also our alternative hypothesis. Then we state our HO and HA. We specify the level of significance, which means we have to identify the alpha. Then identify the degree of freedom. In this case, it will be N minus 2, the sample size minus 2. Then now we can determine the critical values and rejection region. Here we are going to use the T table, which is table 5 in appendix B of our course textbook. So we find the standardized statistics, T equal to R divided by square root of 1 minus R squared over N minus 2. Now we can make a decision now. Remember, we already have the critical value from the T table, and now we find the T value here also. So make a decision to reject or fail to reject the null hypothesis. Now, if the T that we find is in the rejection region, then we reject HO. Otherwise, we're going to fail to reject HO. Then we need to interpret the decision in the context of the original claim. Now, let's see an example. We are using the same advertising expenses and company sales data. We know from this example previously, the R value is 0.9129. We are going to use the alpha value of 0.05. So first thing we need to do, state our HO. rho is equal to 0 or rho not equal to 0. Alpha is given to be 0.05. The sample size is 8, so degree of freedom will be 8 minus 2, which is 6. Then we draw our diagram. So here we have, again, this is two ways, so 0.025, 0.025 to the left. If you add all together, we get 0.05. Now, when we find the t, it was 2.447, so it's to the left negative 2.447, to the right 2.447. So now, let's find the test statistics. When we find the test statistics, we got 5.478, which again fall in the blue area here. So this means we are going to reject HO. Again, the blue area is the rejection area, and the orange area will be accepted and fair to reject. So our final decision will be at 5% level of significance, there is enough evidence to conclude that there's a significant linear correlation between advertising expenses and company sales. Remember, HO means rho equal to 0, which means there's no relationship between the two variables. HA means it's not equal. So if we reject HO, then it means there's a 5%, our alpha is 0.05. So there's 5% level of significance, that there's enough evidence to conclude that there's a significant linear correlation between the two variables, which is advertising expenses and also the company sales. Next is what is a correlation causation. Normally, this is what we learn in statistics. We say there can be a correlation or association between two variables, but there may not be a causation. Example, let's say in Florida during the summertime, ice cream sales goes up. At the same time, shark attack in the ocean risk goes up also because the water get very warm and the sharks, they come close to where human beings are swimming. And also at the same time, ice cream sales also goes up during the summer. Now, can we say that there's a relationship between sales of ice cream and shark attack? Uh, of course, no. So here we have a correlation that during the summer, sales of ice cream goes up, shark attack also goes up. That's a correlation, but it's not a causation. If I take ice cream and I go to the ocean, it's not guaranteed that I'll be attacked by a shark. Or if I get attacked by a shark, I don't think the first thing we're going to do is to buy ice cream. So that's the concept of correlation causation. So here we say the fact that two variables are strongly correlated does not in itself imply a cause and effect. There's no causation or cause-effect relationship between the variables. So if there's a significant correlation between two variables, you should consider the following possibility. Is there a direct cause and effect relationship between the two variables or the variables? Does S causes Y? Or is there a reverse cause and effect relationship between the two variables? That does Y causes X instead of S causes Y? And the third, is it possible that the relationship between the variables can be caused by a third variable? This is what we call the confounding variable. So in the example of Florida, we can say our third variable will be the weather. When the weather is very warm, shark attack increase, ice cream sales increase. So this will be, the third option will be our one. And normally we use the third variable we call the confounding variable or the locking variable. So is it possible that the relationship between the two variables may be just a coincidence? It is possible. So that will be the summary of these lectures. Again, our main focus on these lectures is to learn the concept of, again, linear correlations. Regression, we will move it to our next lectures. So we use correlation to determine if there's a relationship between two variables. Here, the relationship is linear. We also have non-linear. We are doing simple linear regression, which means the independent variable is only one. We also have a multiple linear regression, which means the independent variable is more than one. So again, wish everybody the best and thank you.